Welcome back to Physics 151 Online. Today I would like to give an introduction to frictional forces and drag forces. And in order to understand how we quantitatively treat frictional forces, we need to think about two cases. One is called static friction, which is the kind of frictional force that exists before an object begins to move across a surface. And the other is sliding friction, which is the kind of force that it experiences once it begins to move across the surface. These are related, but they're actually slightly different from one another. So imagine now that we have a block that's on a surface. The block has a mass m, and we exert a horizontal force F on it. Maybe there's a string tied to it, so we very gently begin to pull on this string. Let's think about the free body diagram for this situation. Okay, there's a pulling force F, the weight, which is the earth pulling down on the object. There's the normal force of the surface pushing up, and then there is a force that we will call F sub s for static friction. Now, how do I know to draw that force? Well, I know just experimentally that if I pull on this string just a little bit, I can exert a force on the string and the object will not yet begin to move. And so if the object is feeling a force to the right and yet is not accelerating in that direction, there must be a force opposing that such that the net horizontal force is zero. And that is why I know just from simple experimentation and the use of Newton's second law that such a force must exist even though the object's not moving. Okay, so that's the force of static friction. Now, if there is no applied force F, then there is no static friction force. So it's an interesting kind of force. It only exists when there's an opposing force applied. And eventually, if the applied force, capital F, reaches some maximum value, then the object will begin to accelerate to the right, and that force of static friction will now be slightly different, and we will call that the force of kinetic friction. There still will be a rubbing of one surface against the other, and with the kinds of consequences that you might imagine, there's some heat that's generated when two surfaces rub against each other. But it will be a different quantitative kind of force. So the way that we can summarize the sorts of experimental observations that you can make is through a diagram like this. And what we're plotting on the vertical axis is the force of friction. And we use a lowercase f to represent this. On the horizontal axis, we're imagining that we're plotting the applied force. So if the applied force is zero, the static friction force is zero. As the applied force increases, the static friction force matches it, and it's in the opposite direction, but with equal magnitude, until it gets to a maximum value where the object now begins to move. So on the left-hand side of that dotted line, we'll call this the regime of static friction. Now once it begins to move, when we have an applied force that's greater than this critical value, it begins to slide, and there's still friction, but we'll call that now kinetic friction or sliding friction. And F sub k is what we'll use for that. So, what does that frictional force depend on? Oh, and notice too, one thing about this diagram is it shows the quantitative fact that we notice by doing experiments that it takes a little bit less force to keep an object moving than it does to get it moving in the first place. And so this maximum static friction force, once we exceed it with the applied force, as the object begins to slide, the kinetic friction force is a little bit less than that maximum static friction force. And so that will come into play when we write down the two different equations governing the quantitative relationship for static and kinetic friction forces. Okay, so what does the frictional force depend on? And we can do some simple experiments. Obviously I can't show them here with the PowerPoint, but they do represent the results of real world experiments. If we apply a force, capital F, to a mass m and it begins to move, then we can imagine taking that object and turning it on its side. And so we can look at those two different cases. And what we find is that in both cases, the frictional force F sub k that is experienced by the accelerating object is the same. And so what that tells us is if that object has a different surface area on one side than it does on the other side, it tells us that the frictional force does not depend on the contact area. So that's important. But we can also do a separate experiment and imagine that we now apply that same force F to a mass that's twice as large. What we find out is that we get twice the frictional force. All right? And so what that tells us is that as the mass of the block increases, the frictional force that it experiences when it slides increases proportionally. If you double the mass, you double the force of kinetic friction, and so on. So F sub k depends linearly on the mass, and the reason for that is it depends on the normal force between the block and the surface. And in this simple case, if we were to draw a complete free body diagram for the block, we would see that the normal force upward and the weight downward are the only vertical forces, and they have to be equal to each other in magnitude. So what we find is that if the normal force doubles, then the frictional force doubles as well. And that allows us to write down the approximate quantitative relationship that when there's an object that experiences a normal force from a surface, then the frictional force of sliding friction, if it's moving, is equal to a constant mu, that's the Greek letter mu sub k times the normal force. Mu sub k is the coefficient of kinetic friction. And it is, to a very good approximation, for normal surfaces, approximately a constant. It's not dependent on the velocity of the object. Now this is not a law of nature, this is a simple approximation that we make, but it's a fairly good approximation for objects sliding across surfaces. Notice here, unit-wise, F is a force and N is a force. So mu has no units. It simply represents the proportionality between the normal force and the frictional force. The rougher that two surfaces are when they slide across each other, the larger that coefficient of kinetic friction will be. And most typical values are somewhere between 0 and 1 for the coefficient of kinetic friction. 1 would be a very, very large coefficient of kinetic friction. Now, what about static friction? We showed on the previous slides that static friction increases as the applied force increases up to a certain maximum value. And so we define that maximum value by using a different coefficient of friction, mu sub s. And this is the coefficient of static friction. It still depends on the normal force, right? But this mu sub s is larger than mu sub k because according to experimental observations, the maximum static friction force is larger than the kinetic friction force. So mu sub s, coefficient of static friction, which is larger than mu sub k. Maybe sometimes it's not too much larger, maybe just 5 or 10% larger, but it is recognizably larger than the kinetic friction force. So these two equations represent the quantitative ways that we will treat forces of friction in our simple problems. Notice, just to emphasize this, that the static friction force only equals the maximum force when the object is on the verge of sliding. So if there's an applied force and the object's not sliding yet, the static friction force will always be less than or equal to this maximum value. But in many problems we will be interested in that special case where the object is just on the verge of sliding. And when it's on the verge of sliding, then we can use this equation and say that the static friction force is equal to this maximum value here. All right, here's an example. And I'm not going to solve the problem here, but I'm going to draw the free body diagrams and think through a little bit how the forces of friction are acting in this problem. And it's actually fairly challenging. So here is a block M1 resting on a table, and M2 is resting on top of M1. And then we exert a horizontal force F just on block M1. The surface between M1 and the floor has coefficients of kinetic friction mu sub k and mu sub s, and we'll assume for simplicity that the surface of interface between M1 and M2 has those same coefficients of friction. What we're trying to figure out is if we push on M1 with force F, the two blocks will accelerate together. Now, how much horizontal force can we exert on M1 before block M2 begins to slide across M1? And I think you can kind of imagine how this situation could arise. If you use a small applied force, then M1 and M2 will move together, but if you push too hard, then M1 will move to the right and M2 will slide backwards against M1, and they won't move together with exactly the same acceleration. So what we're trying to do is find what that force is that would cause M2 to slide across M1. Now, free body diagrams are kind of tricky here because, for example, M1, it's in contact with a surface, it's also in contact with M2, and it's experiencing this force F. So let's draw the free body diagram for it. They're kind of tricky in this case, but they're vital to getting the correct answer. So for M1, some of these forces are pretty obvious. There is the force of the surface pushing up on M1. We'll call that the normal force N1. There is the pushing force horizontally, capital F. There is the weight, M1G. But now there are three additional forces acting on block M1. First of all, I've labeled it F sub C here. It's the contact force of M2 pushing down on M1. And you could think of this as a normal force, but I'm not going to draw it that way because I don't want to confuse things. So F sub C is the force of M2 acting on M1 because they're touching. Then also there is the force of the kinetic friction force on M1 because we assume it's sliding to the right across the surface. So it will be experiencing a force to the left that will be the kinetic friction force, F sub K. What about this last force, F sub S? Why is there a force there? Well, it turns out that M2, as we draw its free body diagram, we will see that it experiences a force that allows it to accelerate along with M1, and that is the force of friction between those two surfaces. And as long as M2 and M1 move together, that is a static friction force. So M2 over here experiences a force to the right, a static friction force, and by Newton's third law, there has to be an equal and opposite force that M2 exerts on M1. And that may not be obvious. You really have to think it through. So if M2 experiences a force to the right because of its contact with M1, then M1 experiences a force to the left because it's in contact with M2. So these free body diagrams are actually quite revealing, and they're also pretty complicated. But if you can draw the free body diagrams correctly, then you're well on your way to solving problems involving friction. If it's a little bit confusing, how I know how to draw these arrows, here's how I think of it. The frictional force acts in a direction that opposes what would happen if there were no frictional force. So imagine that M2 is a block of ice, just a cube of ice sitting on top of a very smooth surface. And if we pushed on M1 to the right, if there were no friction between M1 and M2, M1 would move to the right and M2 would just stay in one place. It would appear to be moving to the left relative to M1 if those surfaces that were very, very smooth. And so since we now have a situation with friction, what's happening then is the frictional force acts on M2 to resist that situation. So the frictional force F sub S acts to the right because otherwise, if there were no friction, M2 would appear to slide to the left relative to M1. And I also know that Fs has to point to the right because M1 and M2 are accelerating together, right? So M2 has to experience a net force to the right anyway in order for it to be able to accelerate to the right. So once I have that arrow in place on the M2 diagram, I then realize by Newton's third law there's got to be another arrow acting on M1 that's equal but opposite to this one. Now, I also want to introduce velocity-dependent frictional forces, and sometimes we call these drag forces. These are different than sliding friction forces because they do in fact depend on the speed of the object that is experiencing the force. These kinds of forces are very common for objects that move through a fluid. For example, if we were to take a ball bearing and drop it into a tub of water, and it were to sink down to the bottom of the tub, it would experience a drag force as it moves through the water and falls downward. Even in air, it will experience that same kind of a force, although it won't be as large. But we would like to be able to develop a model and then analyze those kinds of situations where we're not going to neglect air resistance. We're actually going to model it with a simple equation and then see what kind of result it gives us. So imagine a ball launched vertically from the Earth's surface, going upward with a speed v0. Now let's assume that there's a resistive force or a drag force that is opposite to the direction of the velocity. And the constant that tells us how strong that force is will just represent with a constant b. What's buried inside b is some really cool physics. It's going to depend on things like the density of the air, and it might depend on the shape of the ball itself. If that ball is a sphere, then that will influence the value of b. If the ball is ellipsoidal, or if it's not a ball at all but maybe a rock, the shape of that will play into the value that b has. But if we use this simple approximation, basically what it tells us is the faster the block moves, the stronger the drag force. Then we can draw a free body diagram for this ball as it moves upward. So if the direction of motion is upward, then we see that the weight, of course, is downward, and since the drag force resists the motion, then the drag force is b times v in the downward direction. And the minus sign in this equation simply means whatever direction v is, the drag force is in the opposite direction. So that's how I knew to draw it this way. That's our free body diagram, and then we can use Newton's second law and solve it in order to get an expression for the velocity of that ball as a function of time. So we add up all the forces in the y direction, set that equal to mass times acceleration in the y direction, and using the free body diagram, the only two forces acting are both negative. Negative mg minus b times v sub y equals mass times a sub y. All right, now this is a difficult equation. I can't just solve it for v sub y and pretend like I'm done, because although m is a constant, g is a constant, and b is a constant, the acceleration is not a constant. So v sub y and a are both variables in this equation, and it's kind of confusing to know how to proceed. But the way we do this is we represent a in terms of v by writing a sub y is equal to the derivative of v sub y with respect to t. And since I know all of the motion is in the y direction, at this point I'll drop the subscripts just to make the equations a little bit simpler. So all I have is negative mg minus bv is mass times acceleration, or mdv dt. And this, maybe for the first time, you'll be seeing an example of a simple differential equation. It's a differential equation because it relates the derivative of a quantity, the velocity, to the velocity itself. So how do we proceed from here? Well, the method that we're going to use, and you'll have a homework problem that it gives you practice doing this, we're going to use the technique called separation of variables. The basic idea is we take all the terms in this equation that have a v in them and move them to one side of the equation, and then all of the terms that have a t, because it's the other variable, and we move those terms to the other side of the equation. And so first thing is I'm just going to divide both sides by m, so that gives me negative g minus b over m times v is dv dt. I'm getting the derivative all by itself. Now what I want to do is get all the terms that have v on one side of the equation. So let's divide both sides by, well, first multiply both sides by dt. So then I'm going to have this negative g minus b over m times v term, right? And then divide both sides by that. So I'm going to end up, after doing these two steps, with dv over g plus b over m times v is negative dt. And that negative sign just flipped from one side to the other. So what I've done is I've separated the variables. The left-hand side depends only on velocity and some constants, right? So there's a differential, dv, there's a v in the denominator. The right-hand side only depends on time. And so once you've gotten to this point in a separation of variables problem, now you realize that, well, this equation tells me how a differential change in time, dt, produces a differential change in the velocity, dv, but it depends on how large the velocity is. So when I get to this point, I integrate both sides of the equation from some initial value to some final value. In this case, I'm integrating the right-hand side from an initial time, t equals 0, to a final time. So t equals 0 is when the ball begins to move upward at a speed v0, whatever its initial speed is, so that on the left-hand side, we integrate from whatever value the velocity had at time t0, and we'll call that v0, to whatever value it has at time t, and we'll call that v. So both of these integrals are relatively straightforward to do. The right-hand side is especially easy because it's just going to give us a value negative t. The left-hand side, you might look at this and recognize how to do it, but it's going to involve a natural logarithm. And so I'm not going to work through all the steps, but when you do that, just a few short steps later, you can solve for the velocity as a function of time. And it has this relatively straightforward result. We can check this result, like I asked you to do in an earlier homework problem, just to make sure that it gives us physically meaningful answers at time t equals 0 and as time approaches infinity. So let's just check that out. As t goes to 0, or at t equals 0, both the exponential terms become 1. E to the 0 is 1, right? So the second term will completely cancel out, 1 minus 1. The first term will just be v equals v0, and that makes sense, right? That's the velocity value at time t equals 0. So in the other limiting case where t goes to infinity, what happens is the exponentials both become 0, because e to the minus infinity gets smaller and smaller and eventually equals 0. So the first term goes away. The second term, we're left with simply mg over b times negative 1, or negative mg over b, and this says that as time goes to infinity, the velocity will reach a terminal velocity. So if I throw the ball up in the air, it eventually will reach a maximum value and then turn around and come back down. And on its way back down, if it doesn't hit the ground first, so this essentially means it has to be thrown upward so that it goes up for a long time before it comes down, it will reach a constant value. The minus sign means it's falling down, and we call this value a terminal velocity, which means it's the final velocity that the object has on its way back down. And you can see, if you didn't realize it already, that the reason this happens is because as the object falls down, it speeds up and speeds up, which means the resistive force or drag force upward gets larger and eventually gets to the point where the downward force, which is the weight mg, equals the upward force, which is negative bv, right? And so that means the object will no longer accelerate because the net force in the vertical direction will be 0, and it reaches a constant value for the velocity. So this is a good example of how we can use separation of variables to treat velocity-dependent drag forces, and you will have a chance to do this on your homework as well. So I will see you in class.